Hello, everyone. That's a lot of people. Let's do it. My name is Surinder Singh. With my colleague here, Anmol, we're going to talk about how we run stateful workloads at scale on Kubernetes at Lyft. And let's see, what do we have? So rough agenda of the talk is going to be, we'll first define what those stateful workloads are. We'll give some examples. We'll go through some use cases at Lyft. And then we're going to talk about our platform, Flyte. So Flyte is our in-house built platform where we run most of the Lyft's stateful workloads. We do have a full presentation on Flyte at 5:20 p.m. I'll request everyone to go attend that. But for the sake of this conversation, we'll go over the high level. We'll make sure that everyone has a context for the rest of the talk. And then we'll move on to what were the platform goals when we were designing that platform for those stateful workloads. And then we'll move on to what were the pitfalls and learnings we had while running this platform on Kubernetes for almost a year now. And what did we do for the issues we encountered? We'll go over some of the issues which we think will be interesting for everyone. And then in the end, we'll move to our multi-cluster setup. And towards the end, we'll also have some time for questions. OK, what are these stateful workloads I'm talking about? So think of a stateful workload as a job, long-running job, which has some discrete steps. And each step, you want to store some state. And there is some state passing which happens from one task to another. Example could be, think of a Spark or a Flink task running on a cadence, running on a schedule, with, let's say, trigger time being as an input to the job. Another example is a very standard ETL job where there's a raw data. You load the data, you extract, load, and then you put it into a form that can be consumed by other users at the company. And then yet another one is data science pipelines. We have the raw data, we extract features, and then data scientists come and work on models. Once they have a good model, they push it to prod for inferencing. And some examples from Lyft. As you guys know, that by the virtue of what we do, optimization is an important problem for us. And to do good at it, we have machine learning models everywhere for pricing, for ETA, for locations, for maps data. And these models, some of them are really complex. And then the platform was designed so that we can onboard all of these at the same time. So most of these models run on Flyte. There are ETL jobs running on Flyte. Then there are data backup jobs. What they do is they do a periodic backup of the data, a logical replication of the data, with some checkpointing in between. They also run on Flyte today. And then in the end, we also have some giant simulation framework. Why do we have that? Is since I said we run a lot of data science pipelines in the company, and we cannot always run them in prod to see how good they are doing. So we have a very sophisticated simulation system. But sophistication means complexity. And then we actually had a challenging journey to support these simulation workloads on Flyte. So today they run on Flyte like every day, tons of them. OK, moving on. What is Flyte? So Flyte is a platform which was designed to orchestrate machine learning and data workflows. So this was the primary goal, but secondary goal was to also ensure that there is good collaboration, reuse, and performing those ML operations which engineer has to do every day. We wanted to make that super easy for the engineers. Let me go over some of the core features. So I'll just skim through these features, and then we're going to talk about these in the later slides. First one was serverless. We wanted to be serverless. Users should not be worried about what's behind the scene. Multi-tenant and shareable. Operational excellence was a requirement for us because being a very generic platform, we want to make sure that people running on a platform, they can run their things, they can look into things, they can debug, diagnose things whenever they need. Extensibility was important. This was our learning from a previous incarnation of Flyte, where we noticed that anytime we have to onboard a new use case, we wanted to do something special. So we wanted to build a platform where extensibility is a core feature of it. And the last but not the least is the interaction modes. Today we have gRPC REST endpoint. We also have a UI for manual interaction with the system. So some more concepts. Task is the atomic unit of a Flyte workflow. Think of it like a single container task, which could be a Java or a Python program, or it could be a multi-container job. Think of it like a Spark job. When I say a task as an atomic unit, which means we cannot decompose that further. So you use those tasks, you wrap them with what are the resources you need, what is the relationship with the rest of the nodes, and that becomes a node for you. And you take those bunch of nodes, you define a graph, it's called a workflow in our system. And so workflow is a set of nodes, some dependencies between them, and both tasks and workflows can have inputs, as well as outputs. Okay, this is a pictorial depiction of how a graph looks like. On the left, you see an input node, which is the input to the workflow. Then there are arrows going towards right, which means that those nodes on the right, they need those inputs. And then wherever you see an arrow between two nodes, which means there is a dependency between those nodes. This is a UI, but primitive form. We are working on it. And then there are links to logs and other things on the UI, too. OK, let's dive a little deeper. So this is the block diagram of a Flyte system. On the left, you see the user plane component. There is a CLI. There is a Flyte client. There is an SDK to interact with the system. In the middle, there is a Flyte admin. That is a control plane. Even though in this diagram, it seems like it's part of the execution cluster, but it is not. So we made a conscious choice to move our control plane out of the execution plane. On the right, you see are the components of our execution plane, where there is a Flyte propeller, and then the bunch of other operators and services. Flyte propeller is the brain or heart, whatever you want to call it, of the system, where what it does is it goes through each workflow submitted to the system, looks at what is the current state. If there is this action to be taken, it takes that action and stores that state in etcd, and then moves on. Okay. So we looked at the overall picture. There are many components in the system. I don't want to overwhelm you guys with too much details. But for the rest of the talk, the thing which is really important for us to understand is Flyte propeller, because that is the guy who has a single cluster view. So it's running inside a cluster. It is the guy interacting with the rest of the Kubernetes components. And what it does is it looks through all the workflows in the system. It's a standard Kubernetes operator. There is a control loop where it goes through all the workflows submitted to the system, looks at the current state, parses the graph, traverses the graph, gets to the node which is in progress, updates the status, and moves on to the next one. So it keeps doing that in a loop till we have the workflow in the completion state. And it uses etcd as a state store because we wanted something consistent over there. And since you can understand, this is part of the critical path because all the workflows are going to this guy. So this was kind of optimized for more throughput and scale. Okay. And this is the input to the system. So when I say Flyte propeller works on the workflows, workflows are represented as a custom resource. So if you look at the custom resource here, there are nodes. Nodes have names, they are kind, and there are inputs to the node. And then there are bindings. Bindings is a way where you kind of say, this is my relationship of this node with the other node. And then there are inputs. If you just look at the input, you see a structure over there. This is because we have very strongly typed inputs in the system, and most the inputs are today proto-based. And you will see that there are inputs for the workflow as well as for the nodes. The second part of the CRD is the status. Status is not given by the user, but updated by Flyte propeller. As we progress through the workflow, we keep updating the status with more information when we have it available. We update the node status when we have it. We write output directories where we are pushing the output, and any other information we have. So one thing I'll call out, so output, I say we have it available because we actually ensure that when the task runs completely, then only we make the output available. This was needed to avoid partial failures. And we are open source since last month. We have a good integration with a bunch of open source technologies. We have Spark, Jupyter Notebook, Hive, Kubol. And then we also today run on AWS and Google. And there are more things coming. So next is platform goals. I'll ask Anmol to walk you through platform goals and some of the other things.
Thank you, Surinder. Now that we have a good idea of the kind of stateful workloads we run at Lyft, as well as the platform Flyte we use to run them, let's talk about some of the goals we had in mind while designing Flyte. OK, so scale. So stateful jobs usually present a very different set of load characteristics compared to long-running services, in the sense that the load is usually very bursty, as can be seen on the chart on the right. At Lyft, for stateful workloads, we start thousands of containers per minute, as well as we run tens of millions of containers per month. So the next goal we wanted to talk about is multi-tenancy. So again, at Lyft, using Flyte, we have hundreds of users using our system or platform concurrently, running tasks on them across multiple teams. So we want to make sure that there's isolation and fairness in the system. What that means is we want to make sure that one user of the system is not able to impact other users running tasks or workflows at the same time. We also want to make sure that one user or a set of users or a team can only use a small slice of overall resources or computational power of the platform. A couple of other goals we want to just walk you guys through are performance and extensibility. So Flyte has multiple components. There's Flyte admin, there's Flyte propeller, as Surinder just mentioned. So you want to make sure that every time a workflow or a task is getting processed by one of these system components, there's a minimum system overhead. The processing time is minimized. This can be the initial setup time where the user actually, when he or she launches a workflow, the time it takes from that step to the time the tasks are actually running in the system, as well as the transition time between different states of the workflow when it's getting driven by Flyte propeller. Extensibility, we also want to make sure that the platform is easily extensible and allows users to add support for new task types. So in the future, as new use cases crop up and new solutions to those use cases crop up, we want to make sure that users of Flyte are able to just add support for those use cases and those solutions without having to make any platform level changes. Okay, so the last set of goals we want to just quickly walk you guys through are observability and visibility. What it means is we want to make sure users or teams running on Flyte have insight into how many workflows they are running, how many tasks they are running. But not only that, we also want to make sure they have insight into the resource utilization for those workflows or those tasks. For example, if you as a user are running a Spark job which asks for 100 executors with 50 gigs of memory each, but you are actually only consuming 5 gigs or just using 10% of the memory you requested for, we want to make sure you get that insight into that. This sort of also stems into the next goal, which is the infrastructure cost optimization. So once you have insight into how much resources you are actually using, you can actually go and optimize for infrastructure cost. Besides that, even at the system level or the platform level, we are looking at a couple of things to optimize the overall cost, like exploring low-cost pod instances, as well as trying to optimize based on various utilization patterns. Okay, so those were the goals we had in mind while designing Flyte. So now that we have Flyte running in production for close to a year, and we have a large number of Lyft's stateful workloads running via Flyte, let's talk about some of the issues we ran into and some of the learnings we had based on in the last year. Okay, so the first few learnings are around scale when we actually ran Flyte on a single Kubernetes cluster. So the very first issue when we ran Flyte and started onboarding new users is that we started seeing high latency for API server calls. What happened is whenever the aggregate count of Kubernetes objects on the cluster goes beyond a certain threshold, we started seeing that our API server calls like create pod, etc., were really getting hit. So the overall aggregate count of Kubernetes resources can be because of the pods we are creating for various tasks or workflows in the system, or can be the workflow CRDs or any dependent CRDs like Spark CRDs we create for Spark tasks, or any other Kubernetes system level resources like config maps, secrets, etc. Besides this, we also started seeing that when we are running thousands of workflows concurrently, Kubernetes was really garbage collecting completed pods really aggressively. And what this causes is Flyte propeller, which is sort of the brain, and looks at the status of these pods it has spawned, and to basically to drive the workflow from one state to the next. So if it sees that, hey, I spawned these 5 pods for this particular task in a workflow, and these 5 pods are done, it's able to mark the task as done and spawn new tasks or any dependent tasks in the workflow. But when at scale, Kubernetes really aggressively garbage collects or deletes these completed pods or these pod resources, Flyte propeller is not able to consume that these pods have completed, and the workflows ended up failing, even though the pods might have just successfully completed. So these were the 2 issues we saw at the cluster level. We also saw an interesting issue at per kubelet level, which I want to share with you guys. So when we started, we were using large machine instance types. We were using, I think, machine instances with half a terabyte of memory and I think around 60 to 70 CPUs. And some of our workloads or user workloads were really small. They were requesting pods with just half CPU resource. So what ended up happening is the scheduler, the Kubernetes scheduler, ended up placing a large number of these pods on a single kubelet. I think that was around 150 or so pods were placed on a single kubelet. And we started seeing various kubelet level errors and issues because of that. For example, we started seeing cryo errors in kubelet logs, as well as we started seeing out-of-memory errors, even though as far as we could investigate, our pods or the container within the pods were completing successfully. OK, so these were sort of the 3 cluster level issues we ran into. So how did we solve them? So to limit the overall aggregate count of Kubernetes resources or objects in the cluster, we started using resource quotas to limit the number of pods or number of CRDs in a single cluster. Besides that, we also started aggressively garbage collecting our own completed workflows. So these workflows which have completed, there are no more state transitions for them, and they can be safely deleted. So we started aggressively deleting those workflows, as well as any pods, any Spark CRDs, or any other dependent resources that particular workflow owns. Finally, to solve the kubelet level issue we had, we started using heterogeneous machine pools, where some of the instances we chose were smaller ones, some of the instances were larger ones, and overall we were under that pod limit, pod limit of 100 pods per node, which we saw that works fine without any stability issues. OK, so those were the cluster level issues and learnings. Let's talk about some of the state management level learnings we had while running Flyte at scale for these stateful workloads. So as Surinder talked about, Flyte Propeller is an Kubernetes operator which implements a control loop and is responsible for driving each workflow from one state to the next and eventually to completion. So what happened when we ran sort of a load test on the very initial V1 version of Flyte Propeller for the scale we wanted to support, we started seeing that this processing time the Flyte Propeller takes for each workflow CRD was really high and was beyond the sort of SLOs we wanted to expose to our users. So when we investigated this, we saw that this was largely because of the etcd write times for the workflow CRDs, and those write times, etcd write times, were really high. So how did we go about solving them? One of the ways we actually solved it is by implementing a version cache, where we will store the last written version to etcd in a separate cache. And if we are getting an older version for that CRD from Informer, we will just discard it, thereby saving time on processing time, as well as saving time on trying to write to etcd. We also started using updating the CRD using the sub-resource update API, which recently went live in one of the recent Kubernetes versions. So this basically, for some of our workflow CRDs, the spec part can be really huge. We saw that some of our users were writing really complex workflows which had like hundreds of tasks, and the spec in some of these cases can go into MBs. So by just updating the status part of it, we could save writing that spec to Kubernetes to etcd. Finally, we are also exploring trying to offload that spec altogether, especially when the spec is in MBs. If you can offload the spec to something like an external blob store like S3 and just store a reference in etcd, that will actually also help us improve the etcd write times, as well as reduce the overall size of data stored in etcd. OK, so multi-tenancy. So multi-tenancy was one of another core goals for the platform. Isolation and fairness. We want to make sure that the system is isolated and there's fairness across users. So how do we achieve that? Again, partly by using Kubernetes resource quotas. So we enforce quotas on aggregate count of CPUs or memories a user or a set of users within a team can consume in the cluster. But some of our task types we support are external. They are not Kubernetes native. So for those task types, we sort of maintain our own in-memory local resource store, where we will maintain quotas for those for each namespace for those task types, so that there's fairness for those task types as well. Another issue we ran into when we started using Kubernetes resource quotas is that we started seeing that the API server latencies were again very high, especially for the create pod API. For some of the cases, we saw that P90 hitting as large as going into minutes. We investigated this, and what we found that the create pod API call actually invokes all the webhooks you have configured in the cluster, and then only it goes and invokes the resource quota admission control. So this call is really expensive, especially if you have a sizable number of webhooks configured in the cluster, which was the case for us. And this call was actually taking really taking a very high latency. So we were partly to blame for this is because we were sort of, even if a namespace had hit its resource quotas and had, like, let's say, hundreds of workflows in pending, we would still, Flyte propeller, which is responsible for driving that workflow to the next state, will still try to process each single workflow in that namespace and try to create the pods it can create in the cluster. So for these workflows which were hitting resource quotas, we were still trying to issue create pod API calls to the API server every single time we were processing those workflows. So we were not backing off correctly in these cases. So one of the solutions we are actually implementing right now is to maintain sort of a quota cache for each namespace. We will store the namespaces which have hit their quotas in the recent past, and then we can back off for those namespaces. Flyte propeller can just skip processing those workflows for a little bit and back off accordingly. Okay, Flyte system isolation. We also want to make sure that the system components like Flyte admin, Flyte propeller are also isolated from user pods. Especially, you want to make sure that they don't have to compete with user pods when they want to be scheduled or trying to find a node to get scheduled. So the way we achieve this is by using a separate set of reserved nodes with taints and tolerations, and then using node affinity to place these system pods like Flyte propeller onto those specific reserved nodes. So Flyte propeller and other admin components or other Flyte components which are a single pod, which run as a single pod and drive all the workflows in the system. We also want to make sure that there's fairness across users for those components. So the way we achieve this is by using multiple workflow queues and worker pools, maintaining worker pools per namespace in Flyte propeller, so that a particular set of users running in a namespace can only get a small slice of Flyte propeller's computational power. Performance. So performance was another one of our core goals. One of the ways we achieve performance or improve performance of the system is by providing a feature set called discoverable tasks. So what discoverable tasks do is it will just skip expensive task executions and reuse cache results if the task logic and inputs haven't changed. What that means is if you have run the same task in the past with the same task logic and the same task inputs, we will just cache those outputs generated at that particular instance in the past. And if you're running the same task again now, we will just skip that task execution completely and just reuse those outputs generated in the past. This not only helps with performance, but this also helps with skipping expensive computation and improves cost. Some of the other ways we improve performance of the system is by using node affinity, especially for multi-container data-intensive tasks like Spark. We spawn like hundreds or like a large number of executors and a driver, and then there's a data shuffle between those executors and driver. So placing them on the same node or a very small set of nodes helps with the overall performance of the task. We are also looking into implementing a write-through cache for workflow CRDs. This basically helps us reduce the etcd load for gets and updates. Okay, now I'll ask Surinder to walk you through the rest of the presentation.
Okay. So cost. Since we run tens of millions of containers every month, cost is an important consideration for us. So we did a couple of things on cost, and we are also doing a few more things to reduce them further. So when we started last year, we did a stupid mistake of actually using default autoscaler for the cloud, for AWS cloud, which we are using. So the problem there was that whenever we run pods, it will scale up the cluster, but it will never bring it down. The reason being that it just assumes those machines are at your disposal for free and not try to squeeze them into minimum number of nodes. So the natural choice was to move to cluster autoscaler, which we did, and which saw a decent saving, which is almost double. And what it does, it has a greedy approach of putting the pods on the nodes which are already in the system, running some pods, but still have margin to accommodate another pod. So this ran fine, so we were able to increase utilization from 20 to 40%, but still it's not good enough. So the next step was that, okay, even the autoscaler is doing good, it's just that scheduler itself is not good enough. So we started looking into Kube batch scheduler, and we ran it on a load test, but we still have not kind of using it in prod. But I'll share the basic idea behind that. The basic idea is that since we are running batch kind of a load, there are always temporary bursts. We don't want to scale up and scale down all the time, because whenever you scale up, there is a trigger which will scale up. There will be a time for which the machines will be sitting idle before they can go down. Another is that whenever you're scaling up, sometimes you use on-demand instances, and those are expensive. So we wanted to kind of smoothen out those temporary bursts. So what we want is, we want instead of scheduler, like autoscaler, getting more machines when there is a pending pods in the system, we want the other way around. We want a queued state in the system, which means that when there is a queue in the system and the queue is building more than what we anticipated, then only we want to scale up. Like if there is, let's say, a queue of 10, which we're completely okay with, we know it's a temporary burst, will go away, we don't want to scale up. So that's something we are trying right now. We are also defining quality of service classes. So in our system today, there are critical workloads, which means when they come in, they cannot wait. And what we have done there is we have over-provisioned capacity for them. So when they come in, we don't put them in a queue, we just directly schedule them. This works fine. It's just that not everything is critical in the system. What do we do about non-critical workloads? The workloads which come with non-strict deadlines, they can wait in the queue. So what we do over there is the same thing. We just put them in a queue. We know that when the burst will get over, they will be drained off. So that's what we are trying to do with those quality of services. Right now, so it's something we are developing right now is the Spot instance. So in V0, what we are doing is we are putting a separate ASG cluster for Spot instances, which means that, again, the non-critical workloads which can wait, we'll put them in a queue, and whenever we see that there are Spot instances available at a cost, which we are okay with, we'll grab as many as we need, and then we'll flush up the queue. Anmol touched on discoverable tasks. Discoverable task is a way where we try to identify a work by the task logic and inputs. So what we do here is, if we know that this work has been done in the past, we just reuse the results from the task. This reduces the number of duplicate works we do in the cluster. User visibility is important because we always believe that if we give enough information to the users so that they can look into what they are allocating, how much they are using, they will have incentive to go and reduce and optimize the cost for themselves. So this is what we do. We give them resource metrics, resource usage metrics for their pods. Sometimes they feel that, okay, they are allocating more than they need, they go and change their spec. Sometimes they feel that the ROI itself is not good enough for what they are running, they go and optimize the code. Okay, observability. As a platform, there are multiple use cases we support. Observability becomes really important for us. As I mentioned in the beginning, that when we were designing a system, we made a very conscious choice of having a full control plane outside the execution cluster. And what that means is, even though Flyte Propeller is working on a single instance of a workflow, but all the update it makes, they are synchronously pushed to Flyte control plane, which is Flyte admin. And the reason for that is the guy all the users talk to. There is a UI which is powered by that. There are SDK. And then another thing we did was we actually identify a workflow as a type, there is a name to a workflow. When you're iterating to the workflow, there are revisions. You can look at the historical information of a workflow. You can look at when things went south. You can improve on things. So that is everything. That everything is powered by our control plane. Metrics was another important thing for observability. Today we have two things in place. One is the system metrics, your resource usage and utilization metrics, coming via Prometheus, now SignalFx. Then we also have a statsd setup in the cluster, and that is for user metrics. So whenever we are starting on container, we are giving them a hook into a statsd daemon set. So there is a statsd daemon set wrapped by a statsd service. So all the user metrics, they are labeled correctly, and then they flow via statsd to our wavefront cluster. Okay. So far we have talked about what were the issues, what were the optimizations we have done for a single cluster. But again, single cluster was not enough for us because of the scale which we run there, we need more than that. So we started with a multi-cluster setup. So Flyte admin, which was never part of execution cluster, now can talk to multiple execution clusters. So when you start up a new cluster, you just tell Flyte admin about, this is my new cluster. And then you also set up some load balancing policy. Load balancing policy could be, I want to distribute based on these weights, or let's say I want to say this workflow needs to be run on a cluster which has a certain label. You can do all of that through a load balancing policy. This works fine. This gives us a very fault-tolerant system where when we see things are going bad, we just remove that cluster out of the whole system. We are in fact trying to build a pipe feedback back to the Flyte control plane where it auto-discovers that the cluster is not doing good. It will stop giving work to that cluster and move on to other clusters. This was all good. Actually, by doing this for scale, we also got something interesting out of it, which was we are able to push incremental updates. Whenever there's a risky change in the cluster, rather than pushing it to all the cluster, we push it to a small cluster, we ramp up the traffic, and then when we are confident, we just take it out to the clusters. We also see yet another advantage with multi-cluster setup. This is like there are some users who want performance, but at the same time, some security, additional security. Let's say there is a user who doesn't want to pull that image all the time. They want to use the cache container image, which means there's a security problem. But what we can do over here is we can ask them to have a separate cluster, and then Flyte admin will handle the redirection of the traffic to that cluster. OK, that's it from us. We have a full detailed talk on Flyte at 5:20 p.m. We have most of the Flyte team sitting here. We would like to know your use cases. Come talk to us. And then more information about us is on flyte.org. Thank you.
Thank you, Surinder Anmol. We have a couple of minutes for questions. 2, 3 questions. There's a mic over there. I have a mic. Wave your hand, and we will come to you so that the question can
There's one on this side.
Hello. How would you address the advantage of Flyte against Argo workflow or some other workflow engines?
Yeah, so I can answer that, but I would strongly suggest coming to our full detailed talk because I don't want to summarize the answer in 1 or 2 lines. We have a talk at 5:20 p.m. Please come to us, and we can also talk offline about it.
Good. We have a question here on the right-hand side.
We also have some Flyte stickers. If you guys are interested, please come by the stage.
Yep.
I got a quick question. Are they?
Anmol.
Yes. Yeah, quick question. You guys mentioned you're capturing resource constraints for memory and CPU number of cores. Do you do anything for like long-running jobs that are running too long?
So we have a thing of so today in the system, if you specify a timeout and you say, I want the job to be running for 2 days, we are OK with it. But we generally encourage people to write small tasks so that if they die, they don't lose that work. But we do have those ones running today.
Good. I think we have time for one more short question. Good. Right here in front.
Hi. It sounds like there's some workarounds for some performance bottlenecks in etcd. Has that been communicated to etcd? Are there known limitations or? So
we have seen 2 things, right? One is if we just increase our writes to etcd, the etcd just slows down. So that's something which I think is a known thing. Another is the overall size stored in etcd. When we see number of objects in the cluster, they're going up, or our own Flyte workflow sizes grow up, we see a problem over there. So we see a 2-side problem. When the request count goes up, and then when the overall storage goes up. So we are trying to kind of reduce on both. So we don't want to do a duplicate write, but at the same time, we also want to reduce the object size.
I'll add something to that. So at some point, there is an abuse of etcd, and at some point, it's like the right level of SLA that you want from etcd. I think we still think that we are at the abuse category, and we want to bring it to the right. And I think there will be certain things that we'll push forward to etcd. We would love to.
Good. Thank you. It's time to conclude the session. And big applause to Surinder and Anmol.
Thank you.
Thanks, guys.